Assalamu alaikum, hello and welcome. In this lecture, we will be discussing about the microprocessor programming model and architecture. Programming model and architecture are two very important things when we are thinking about the microprocessor and when we are doing assembly language programming. So, in order to understand the microprocessor and all the things that go on inside the microprocessor, this low-level discussion is a really nice discussion that would help us clarify many points regarding as per our discussion. So of course we look at the concept of registers, and registers are connected by buses, and we also have the tri-state buffers, right? And tri-state buffers are important because they have an input state and output state, and the third very useful high impedance state. As you can see from the word high impedance means practically a short circuit. So when the tri-state buffer is in a high impedance state, it is behaving as a short circuit, so nothing is connected at the output of the tri-state buffer, right? So the input is not connected to the output and it's physically an open circuit. So this state is used a lot. This is a very useful state. So this figure 2.18a from the book KL Short is an excellent diagram because it describes the low-level functioning of the microprocessor's data path, right? We have the source registers W, X, Y and Z. These are connected through the high impedance tri-state buffers, tri-state buffers given by these four tri-state buffers, and these are the activation signals for the tri-state buffers. For example, if RDW bar is 0, it means the output Q from W is connected to the data bus. And if RDW bar equals 1, this tri-state buffer is in a high impedance state and this behaves as an open circuit and Q is not connected to the data bus. So for example, if you want to read the source register W, what we would do? We would set RDW bar to 0 so that the output of W, which is Q, is put on the data bus. Similar is the case for the other signals in the other registers. Please mind that at one time only one register should be read on the data bus, otherwise there would be confusion or loss of signals. So either it is none of the registers are read, or either it is one of the registers that are read. And what are the registers that can be read? W, X, Y and Z. On the other hand, on the right hand side, we have the destination registers M, N, O and P, and they are driven by these signals W, R, M bar, right? So what do we mean by that? If W, R, M bar is 0, whatever data that is present on the data bus would be logged onto the D flip-flop M, and so on and so forth, right? So whatever the contents of the data bus can be logged onto the respective destination register by setting the respective clock signal to 0 and then 1 to complete the process. So now, as we know that we can read one of the source registers or we can read none of the source registers, it is an ideal candidate for implementation on a 1 out of 4 decoder, right? So if the decoder is enabled, whatever is the binary code over here, that particular signal would be low and that particular source register would be read. For example, if RD bar is 0 and A0 and A1 are also zeros, it means RDW bar would be 0 and all other signals would be 1s. So when RDW bar is 0, this buffer, tri-state buffer would be in a low impedance state enabled. The output Q would be read on the data bus. Similarly, for selecting one destination out of the 4, we again use 1 out of 4 decoder. It means when WR equals 0 and if B0 and B1 are also zeros, it means WRM bar signal is 0 just like previously, and all other signals are 1s. So if WRM is 0, the content of the data bus would be written on the M register. So as you can see, information flows from the left hand side to the right hand side. It is always read from the left hand side and written on the right hand side. You cannot go the other way around. You cannot read the destination register and write on the source register. So it is basically a unidirectional data bus that we are talking about. So now we have this diagram and we can look at as per the development of the previous figure, which is this figure, right? So one thing that we notice that if RD bar is 1, what would be the output of the decoder? It would be all ones, right? So the output would be all ones if RD bar is 1. Similarly, if WR bar is 1, again all these outputs of the decoder would be all ones, and this is basically the case when the right signal is 1. Okay. So if RD bar is 1, it means no source register is going to be read. Similarly, if WR bar is 1, no destination register would be written. So this is an important point, in fact. So let's see this diagram. Let's examine this timing diagram, right? It's an interesting diagram that we can see. And we can sort of see, right? So what's happening in the first phase? In this first phase, the RD bar signal becomes low at this point, right? So when RD bar signal becomes low at this point, it means that this decoder for reading has been enabled. So we are talking basically about this side. So now when RD bar is 0, we see what are the contents of A0 and A1, right? So we see that A1 is 1 and A0 is 0. So 10 is the address that is applied to this decoder, right? So as we see that when 10 is applied to the source address, it means we are trying to read the register. Why? Because when 10 is applied, this signal would be 0 and all other signals would be 1s. So we say that the Y is read and the data of the Y register is placed on the data bus. A little time afterwards, the WR bar signal becomes 0. And when WR bar signal becomes 0, we are talking about now this decoder, which is the destination decoder. And for the destination address, we should look at the B0 and the B1 signals. So the point when WR bar becomes 0, we look at the contents of B0 and B1. So right, we can see that at this point B1 is 0 and B0 is 1. So B0 is 1 and B1 is 0. It means 0, 1 is the destination address. So when 0, 1 is applied on B0 and B1, so 0, 0, 1 applies that the register N is written. So as we can see, Y is read and N is written as the destination register. Similarly, we can look for other combinations and other things. I would invite you, the students, to please verify this statement as per the control signal as a home exercise. Now, we have seen that the left hand side registers can only be read because of these output signals, and the right hand side signals can only be written because of these write signals, right? So how can we convert this unidirectional data bus into a bidirectional data bus? Any suggestions? What can be done? If we include the writing signals on this side and we connect the output of the destinations by virtue of the tri-state buffers onto the source registers like this, so we have the information for the bidirectional data flow. So what do we mean by that? We can see that now basically the output signals have been connected by the tri-state buffers on the right hand side, and the input signals have been included on the left hand side for writing of W, X, Y and Z. So I can say that W, X, Y and Z can be read as well as written. Similarly, M and OP can be read as well as written. So information can flow from left hand side to the right hand side, and this would happen when any one of this register is read and when any one of this register is written. And also on the other hand, we can read any of the registers on the right and write any register on the left. So in that case, when the right hand side is written and the left hand side is read, the information flow would be on the opposite direction. So now we can see that we have a bidirectional data bus. What about the decoder? The decoder for reading. How many outputs would the decoder for reading would have? 4 or 8? 8 is correct. 1, 2, 3, 4, 5, 6, 7, 8. Similarly for writing, we would also have the 8 inputs. 1, 2, 3, 4, 5, 6, 7, 8. So 1 out of 8 decoder would be used for selecting one of the source registers, and 1 out of 8 decoder would be used to select any one of the destination registers. So this is the case now. And as we know that as we are using 1 out of 8 decoder, we must now use 3 bits for the address, source address, and 3 bits B0, B1, B2 for the destination address. Source address generates the read signals and destination address generates the write signals. And this is basically the truth table now. As we can see that any register can be read or any register can be written. So this combination, this is a unified combination now. If A0, A1 and A2 0, 0, 0, we are reading the W register. If B0, B1 and B2 0, 0, 0, we are writing the W register, and so on and so forth. Write decoder inputs A0, A1 and A2 and B0, B1, B2 if we want to read W and we want to write to the P register. Right? So if we want to read W, the source should be A0, A1 and A2 should be 0, 0, 0. And if we want to write to the P register, B0, B1 and B2 should be pointing to the P register. Means B0, B1 and B2 should be all ones. So A0, A1 and A2 would be 0, 0, 0 and B0, B1 and B2 would be 1, 1, 1 to read W and write to P. Now some important terms that are very important. Programming model refers to all registers of the microprocessor that can be manipulated using software. So all of the registers that you can manipulate and that you can change using software forms the programming model of the processor. And what is the instruction set? Instruction set is an encyclopedia of all possible instructions of a microprocessor. So if you want to do low-level programming, especially in assembly language, so you must have the idea, vivid idea about the programming model and the instruction set. Unless you have an idea about the programming model and instruction set, you cannot do assembly language programming. Let's now look at the programming model of the 8086 and above processors, right? As far as the 8086 is concerned, we have the 16-bit architecture. So we have the general purpose registers AX, BX, CX, DX, the base pointer register, source index, destination index, and stack pointer register, right? Now when we move on to the 32-bit architecture, we have the enhanced prefix. So EAX is a 32-bit version of AX. Coming to think of it, AX is a 16-bit version. It is divided into two 8-bit registers, AL and AH, A lower and A higher. So this 8 bits combined with this 8 bits form the AX register. And when we talk about the core architecture, which is 64 bits, so Intel uses the R prefix. So RAX is a 64-bit version of AX. Similar is the case for the other registers that have been shown. And of course, in the core architecture also have these R8, R9, R10, R11, R15 special registers that are reserved for the core architecture, right? Then of course we have the flags register. Flag is a very important register that is used for seeing the effect of mathematical operations. E flag is a 32-bit version, and R flag is a 64-bit version. Similarly, instruction pointer IP is a 16-bit version of the register, EIP is a 32-bit version, and rest in peace RIP is a 64-bit version of the instruction pointer. Then we have the code segment, data segment, extra segment, stack segment register, right? Then we have of course the FS and the GS, global segment and FS registers. We will be talking about them later on when we talk about the other architectures above the 8086. Now a quick review. Multipurpose registers. RAX is the accumulator. Accumulator is referenced as a 64-bit register when it's called RAX. A 32-bit register EX, 16-bit is AX, and either as two 8-bit registers AH and AL. So an accumulator is used for instructions such as multiplication, division, and some of the adjustment instructions. And AX is also a general purpose register. Hence the AX is termed as a multi-purpose register. It is a general purpose register as well as an operational register because it carries out multiplication, division, and some of the adjustment instructions. Similarly, RBX is the base index, and again it is addressable as 64-bit version, 32-bit version, 16-bit version, or two 8-bit versions BH and BL. So BX register holds the offset address of a location in memory system in all versions of the microprocessor. We will talk about segments and offsets as we move along. This is an important concept in the Intel family. Similarly, RCX is the count register, again true 64-bit version, 32-bit version, 16-bit version, and 8-bit version. And it holds the count for various instructions like shift, rotate, and loop. So loop is a very important instruction that we can carry out, and it's a very important instruction that can be used. For example, we can have something like move CX, 5, and then we can have a label, and the label can have the instruction move AX, BX, and then we can carry out loop L1. So what would happen? We have initialized the loop counter for 5, and this is the loop label that we would be looping to. So we execute this instruction. When the loop instruction is encountered, CX is decremented by 1. So CX becomes 4, and it is compared to 0. Since 4 is not equal to 0, we move to this loop. Again execute the body of the loop. This is the body of the loop. And then again CX is decremented to 3. Again 3 is not 0, so we again move on to L1. CX becomes 2. Again we move to this loop. Decrement. CX becomes 1. Again we move to this loop. Now when we decrement Cx, now Cx becomes 1 minus 1 or 0. Now since Cx is 0, we don't go to L1, we execute the next instruction. So loop instruction can form as a loop counter. It can be used as a loop counter. RDX, again a very nice acronym. It is the data register. Again same addressing, 64, 32, 16 and 8 bits addressing. And it holds part of the result from multiplication or part of the dividend before division. So in the classical 8086 operation, when two 16-bit numbers are multiplied, the result is 32 bits. And that 32-bit result is stored in combination of DX and AX. DX holds the upper 32 bits of the result and AX holds the lower 32 bit of the results.